One of the most important ideas in all of statistics is the normal distribution, or the bell curve. We see this everywhere. We will use it all the time when analyzing data, so we need to understand this. So, a normal distribution is when we find a population is distributed following a bell-shaped curve. So if I make a histogram of it, I'm measuring heights or weights of people or something like that, and if I do this, I find that the histogram follows kind of a roughly bell-shaped curve with a single peak in the exact center. Lots of people are relatively near average height, and then fewer and fewer are found to be unusually tall or unusually short. A true normal distribution, a perfect normal distribution, is going to be perfectly symmetrical, so that the mean, the average, is exactly equal to the median, the middle, which is exactly equal to the mode, the most common. So the most common height is also the average height, which is also the median height. Every normal distribution, in a way, is relatively simple because it can be described with exactly two numbers. If you tell me these two numbers about a given normal distribution, I know everything there is to know about it. Those two numbers are the mean, which we represent with the Greek letter mu, and the standard deviation, which we represent with the Greek letter sigma. So mu, the mean, tells me where the center, the middle, the peak of the normal distribution is. Sigma, on the other hand, the standard deviation, tells me how wide the normal distribution is. A large value of sigma, a large value of standard deviation tells me, for instance, in this case, the heights would be very widely distributed. A small value tells me, no, the heights are all closely bunched up right around the middle value. Normal distributions are found everywhere. I mean, this is one of the most important discoveries in all of the history of science. Human beings' heights, if I want to study the velocities of atoms in a gas as they bounce around, I find they follow a normal distribution. If I study the lifetimes of light bulbs, and I make a histogram of that data, measuring the lifetimes of hundreds and hundreds of light bulbs, I find that they follow a normal distribution. If I study loaves of bread being produced by a bakery, and I measure the weights of lots of them, it follows a normal distribution. If I study the sizes of snowflakes, if I study how the number of customers at a restaurant varies over time, if I study the velocities of galaxies in a galaxy cluster far across the universe, if I study the thickness of bark on different trees in a forest, all of these things I find follow very closely a normal distribution, this classic standard bell-shaped curve. Why? So we find this all over the place. Here's another example of a normal distribution. This is data that shows the diameters of 323 black locust trees as measured in a forest in Poland. It's amazing. It's incredible. Why would this happen? When we measure different measures of population, we make a histogram, this pops up in nature again and again and again. This is a ubiquitous curve. It happens. It's a law of nature. How come? Here's another example. Look at this. Here we have the heights of 3,000 adult English male criminals measured around the year 1900. And there's the height. There's that beautiful normal distribution. This is a mathematical law, and it pops up all over the place. We find it in physics, in astronomy, in biology, in chemistry. This is an amazing, amazing thing. How in the world can one mathematical distribution, one formula, one equation for one specific type of curve apply to such an enormously diverse range of phenomena all across our universe? That's an interesting question. So let's do the history of this. I mean, this is one of the most important discoveries in the whole history of science. This starts with Abraham de Moivre. He was a French mathematician, good friend of Isaac Newton way back in the 1600s, back in the day. He got interested in randomness and chance, and he actually wrote a book about probabilities, which was said to be prized by gamblers. So he's studying probability and randomness. He's studying the problem of, say, like flipping a coin. Okay, so like a simple event where I'm going to flip a coin and I do it again and again and again, and every flip is independent of every other flip. And what if I find, if I flip a coin 10 times, what I find is, well, the most common result is to get 5 heads and 5 tails. Sometimes you're going to get 6 heads and 4 tails, or sometimes 4 heads and 6 tails. And so the most likely result is 5, and then you see less and less likelihood of getting something like 7 heads, or 8 heads, or 9 heads. So we get this kind of distribution, this kind of mound-shaped, bell-curve-shaped distribution. So what if I flip a coin 100 times? Now, back in the day, mathematicians had figured out ways of computing things for, 5 coin flips and 10 coin flips and that sort of thing. If you start getting to like 100 coin flips, the equations just got ridiculous. They got annoying, they got complicated. So what de Moivre did was he figured out a way to approximate what is this distribution of all these heads and tails, what is that approaching if we have very large numbers of coin flips? He discovered the normal distribution. He found the formula. He found that as the number of coin flips grows very large, the distribution of heads approaches a very specific, particular curve. He was the first person in history to discover the normal distribution and showed that how this, in his book, he showed how this could be used to estimate things like rolls of dice and flips of coins, but he had absolutely had no idea what he'd discovered. He had no idea that he had had tiger by the tail. All right, so history goes on. 100 years later, this fine gentleman, this is Giuseppe Piazzi, he discovered the asteroid Ceres. He observed it. He's the first person ever to discover any asteroid, and he's looking out there with his telescope. He observes it for 6 weeks. This is an exciting, important discovery, but then, oh dear, he loses sight of the asteroid as it goes behind the sun, and the 6 weeks of data isn't enough to figure out the orbit of Ceres, and so astronomers all across Europe are trying to figure out where should we look. In a couple of months when this thing pops up from behind the sun, where are we going to find it? Let me introduce this fine gentleman. This is Carl Friedrich Gauss, one of the greatest mathematicians in all of human history. He was 24 years old and he was doing amazing stuff already. He worked on this problem for 3 months. How can we learn as much as possible from the observations made by Piazzi? One of his key ideas was that Piazzi's measurements were imperfect. They had errors to them. And so the measurements, if you took every single one of Piazzi's measurements, they're not going to fit an orbit perfectly. So he needed to know the distribution of the measurement errors that were likely to happen as this astronomer was measuring the location of this asteroid. And using this, he derived the normal distribution. He found the bell curve. Again, as a result, he became famous. And to this day, if you look at German money, you can find that this note has Gauss right there, and just to the left of his face is the normal distribution that he described. As a result, often in astronomy and physics, we'll call the normal distribution, we call that the Gaussian distribution in his honor. But again, he was thinking of this as being an error distribution of measurement errors made by a scientist. This is fascinating. This is interesting. De Moivre and Gauss both independently discovered the normal distribution, and neither one really had any idea that they had discovered an important, vital, fundamental law of nature. De Moivre is talking about approximating lots of random events like coin flips. Gauss is talking about measurement errors of scientists. Neither of them would have expected, for instance, the velocities of galaxies to look like this. Look at this beautiful normal distribution where you've got groups of galaxies orbiting around each other in clusters. Why does this happen? All right, the next person we need to talk about is Adolphe Quetelet. He started out training as an astronomer, but then got interested in the social sciences back in the 1800s, and he read an article from 1817 presenting data on the chest measurements of 5,738 Scottish soldiers. Now, why exactly anybody would measure the chests of 5,738 Scottish soldiers, I have no idea, and I don't know why they would do that, but whatever. They did that, they published the results. Quetelet realized that these measurements were distributed in the same way as errors in astronomical measurements, as described by Gauss. He published a book in 1846 where he showed this analysis, and he showed that the techniques that astronomers and physical scientists were now using to deal with their measurement error could now be used in the social sciences. He did all sorts of cool things. He coined the term the average man. His ideas were adopted by the young field of the social sciences, and people began to realize that you could find these bell-shaped curves, these normal distributions, all over the place. So, the normal distribution can be described by precisely and exactly two numbers, the mean, the average, and the standard deviation, the width. You tell me these two numbers, I know everything there is to know about a normal distribution. Every normal distribution is perfectly symmetric. That means exactly 50% of the data is above the mean, 50% is below the mean, which is why for a normal distribution, the mean equals the median. So the mean tells us where its center, where that central peak is. If you got a larger mean, you're going to be farther to the right with bigger numbers. If you have a smaller mean, you're going to be farther to the left on a histogram with smaller numbers. The standard deviation tells me how wide it is. A big standard deviation has a lower peak and broader wings going out to the side. A small standard deviation is going to be more peaked toward the center. The smaller distribution, everything is very, very close to the mean. In every normal distribution, further, there's an interesting distribution of how the data is laid out. Every normal distribution, whether I'm talking about trees, Scottish soldiers, or galaxies, 68% of the data is going to be within one standard deviation of the mean. So if I find the average and I go one standard deviation above and one standard deviation below, 68, about 2/3 of the stuff, will be within that range. If I go 2 standard deviations out, 2 standard deviations above the mean, 2 standard deviations below the mean, I will catch 95% of the distribution. 95% of the data will be within 2 standard deviations of the mean. And if I go out to 3 standard deviations, that's going to catch almost everything. 99.7% of all the data in the whole distribution will be within 3 standard deviations of the mean. This is a general rule that applies to all normal distributions. We can quantify where we are relative to the rest of normal distribution with a z-score. A z-score is a number that tells me how many standard deviations above or below the mean value is. So suppose I've got some value. I've got a height, a velocity of a galaxy, a width of a tree, something like that. I have a value. We'll call it x. The z-score will tell us how far above or below the mean is. If I'm right on the mean, then my z-score is going to be 0, because that's exactly where the mean is. If I'm above the mean, I'll have a positive z-value. If I'm below the mean, I'll have a negative z-value. If and we compute z-scores as I take my value x, I subtract the mean, and then I divide that difference by the standard deviation. So, for example, systolic blood pressures have a mean of about 130, standard deviation of about 10. So, supposing my systolic blood pressure is about 150. What's my z-score? Well, I take 150 minus 130 to get 20. 20 divided by 10 is 2, and that tells me I have a z-score of 2. That means if that's my blood pressure, then my BP is 2 standard deviations above the mean. On the other hand, if I've got a z-score and I want to go back to a raw score, I can go the other way. I can compute the raw score, the actual value, by taking the mean and adding z times the number of standard deviations, because that's what z is. Z is the number of standard deviations above or below the mean I've got. So again, systolic blood pressure, mean of 130, standard deviation of 10. So for example, suppose somebody has a z-score of negative 0.6. Well, that means this person is 0.6 standard deviations below the mean. What would this person's blood pressure be? Well, we take the mean, 130, we subtract negative 0.6 times 10. Negative 0.6 times 10 is negative 6. So that means this person is 6 blood pressure points below the mean, so that makes it 124. So therefore, my systolic blood pressure would be 124. So, why are normal distributions everywhere? Why does this happen all the time? Why is this a law of nature written into the very fabric of the universe that we find describing galaxies and molecules and everything in between? The reason why this happens is something we mathematicians call the central limit theorem. Okay, so first of all, what is the word theorem? A theorem is a statement that is mathematically true, that I can prove that it's true using airtight, deductive logic. Once you have proved a theorem to be proved, it is true forever. You can go back to the theorems proved back in ancient Greece by Pythagoras and Euclid and those guys. Those theorems are still just as true today as they were back in the day. They're true forever because we use logic. We use airtight deductive logic to prove these things. The central limit theorem, one of these. So the very initial work on the central limit theorem, of course, goes back to Moivre and his work on probability and gambling, but a lot of work was done after that. So, here's ultimately what the central limit theorem says. We're not going to work through the whole proof of it, but the central limit theorem is an amazing, powerful mathematical discovery. It says if we add up many, many, many random numbers, and they are all independent of each other, they're independent of each other, every single one is uncorrelated to all the others, they're all just from the same big distribution, then no matter what that distribution is, the result, the sum, will be normally distributed. That's astonishing. That's amazing. This is the greatest miracle in all of statistics. Every data point we put on our histogram must be the result of adding up many unrelated numbers from some underlying random distribution. And that's why the normal distribution is so universal. That's the central idea behind it. So here's a couple more normal distributions. There we have the heights of NHL hockey players. Here we have the birth weights of 32 lambs. Both of them form this kind of mound-shaped, bell curve-shaped distribution. The reason why the central limit theorem causes the normal distribution to pop up so often is because so many different independent factors go into these things and are ultimately added up in one way or another to get these results. The heights of a hockey player come from, genes, nutrition, experiences in childhood, I don't know, all sorts of different things go into that because so many different factors affect the final result, we end up with normal distributions again and again and again and again. And we're going to use this a ton in this class. Whenever we randomly survey a large number of people and we add up the results and take the average. Taking an average involves adding things up, and if we have a simple random sample, lots and lots of independent things, well, that means every time we take an average, the central limit theorem applies. As long as we have enough people in our sample, and it turns out we're going to need about 30-ish, we will find that we can use the normal distribution to analyze our results even if the underlying distribution itself is not normal itself. This is interesting. This is amazing. This is incredible. So normal distributions are used every day to analyze things like political surveys, consumer surveys, opinion polls, who are you going to vote for, all that sort of thing. All those are analyzed with the equations of the normal distribution, that same normal distribution that came from those guys, from Gauss and from Moivre and all those guys. We still use those today to analyze all sorts of survey results and all sorts of data. Now, the normal distribution, I don't want you to start thinking that everything is the normal distribution. It is common. We find it lots and lots of places, at least approximately, but there's also a lot of data out there which is not normally distributed. So I don't want you to expect that all data is forever and all times normally distributed. That would be too much of an error. With a true normal distribution is perfectly symmetric. 50% above average, 50% below average. If I look at this histogram, this is a histogram of household incomes, and I find that this is not perfectly symmetric. Turns out that, there's a mean somewhere around there. And then as we go to the right, we find a tail going off. We got the very rich off to the right. And as we go to the left, well, it kind of ends at zero because, most people have a positive income. So as a result, we have a skewed distribution. It goes farther to one side than another. This happens a lot where we see something that is approximately normal, and then oftentimes we'll see skew going on one side or another, and then we have to make adjustments to that. So there we go. We have these skew distributions. Here's data from a chemistry experiment where we have, no, that's not a normal distribution. And the tail goes farther to the right and is cut off to the left. This happens a lot as well. We're going to need to learn to look at these different sorts of data and to try to make sense of these. And this is what statistics is all about. The discovery of the normal distribution, more than anything else, that heralds the birth of the science of statistics. This is a field of research where we learn to make sense of data. And the first tool, the hammer, the most common tool we can use is the normal distribution because it happens so often. If we don't have normally distributed data, there are lots and lots of methods. I mean, statisticians are all over the world developing different methods. That's a whole field which we call non-parametric statistics. We're not going to dig into that too much in this class, but I want you to know that it's out there. If you're ever gathering data and you find that it's not normally distributed, that doesn't mean we give up. It just means that, well, there are other tools and you have to dig a little deeper and you have to find the right tools to analyze that sort of data. All right, quick summary. Normal distributions are everywhere, from human heights to velocities of atoms and galaxies and everything in between. Abraham de Moivre discovered an equation, but he used it just as an approximation to describe the distribution of things like coin flips and dice rolls. Carl Friedrich Gauss, he independently discovered this in order to find the asteroid Ceres and was studying it as a distribution of errors made by scientists in their measurements. Quetelet found that this could describe human measurements, and then the floodgates broke open and people realized that this is an amazing, useful thing that we find very, very commonly in in nature. The central limit theorem is the explanation for why it is so common. If we add up many, many, many independent random terms to get a sum, and we do this many times, we find that the distribution of these sums will follow a normal distribution.